All right, welcome. In this video, I want to revisit the algorithm for integer multiplication. This is one we took a quick look at in an earlier video, but I want to revisit it because I want to once again apply our divide and conquer design strategy to show how Anatoly Karatsuba improved on the grade school or the well-known integer multiplication algorithm. So to do that, let's revisit the problem and the algorithm that we're already familiar with. So again, just stated formally as an input and output criteria, we're going to have two integers. We're going to restrict ourselves to integer multiplication here, n and m. And of course, we just want their product. So here, n times m is simply expressed here, the product of n and m. Now, I have expressed n and m here as capital N and m. And again, this is sort of a convention that we use to remind ourselves and our readers that the value of this number is considerably bigger than the size in terms of the number of bits it takes to write down the number. Now remember, when it comes to our algorithms, we're concerned on the input side. So we don't want to confuse ourselves and say that n is n big. That's not true. If we want to consider how many bits it takes to write down, if capital N is our value, then lowercase n equal to the floor of log n plus 1 is the number of bits it takes for us to write down that number. And that's what we're going to take as our input size. So we're actually going to assume lowercase n to be logarithmic in the value of n. And we could do the same thing for m here as well. But for simplicity in our analysis here, we're just going to assume n is the maximum size of either of these two. So if one is greater than the other, typically what we will assume here is that we'll pad up the other one. Maybe m is the smaller one, we'll pad it with zeros to make it the same size as n. And then while we're doing that, to be maybe again a little bit simple, we're going to assume that the number of bits that we're going to actually write down here is also going to be a power of 2. So while we've padded, maybe m with zeros to make it larger to match the size of n, well, if the size of m and n is not a power of 2, we will just add more zeros onto the front to make it a power of 2. Now this is going to be helpful for us in a moment. It's going to allow us to ignore floors or ceilings when we start dividing by 2. Okay, let's revisit our grade school algorithm and consider how many operations it's going to take for us to carry that out. So if we're going to do our grade school algorithm, binary math is actually a little bit easier since we only have ones and zeros. But again, if we're doing our multiplication, we're going to take one bit at a time here. So multiplying the first bit, we're going to get 1101. And then remember, we have to bit shift over. Now we're actually multiplying with zeros, and of course we don't usually have to write down all the zeros here, but we would get all zeros. And then in the next step, we pad by 2, and again we multiply our 1 here, 1, 0, 1, 1. And maybe I'll just jot down the last set of zeros all padded over by 3. What we'll notice here is the n I've selected here is 4. And the number of intermediary products, maybe not surprising, is also going to be 4. Now the size of these products is at least 4, but we added on 3 here, and in fact the last one will be of size 2n minus 1, which is 7 in our case. Now we can add these up. What's that? Another 0, carry, 0, carry, 0, carry, 0. Get something like this as our solution. Well, it didn't actually carry over, but if we got lucky enough with our carry, we could have added one more bit on there if we needed to. bringing us at most up to this 2n value. But we now want to think about how many additions we carried out here. So to compute these products here, I said there was 4 intermediary products. Well, to compute each one, look at the first one, we did 1, 2, 3, 4 bitwise products. So this is about 4 times 4, or 16, or thinking that n is 4 here, we're going to do about n squared multiplications to arise here. Well, again, since this is n going down this way, and we said it was 2n minus 1 going that way, the number of bits in here is also order of n squared. So we're also going to do about n squared additions. So and here when I'm talking about additions, again, I mean bit additions, not the whole value additions. So this is 4 additions, but to carry out those 4 additions, there's many bit additions that we need to carry out along the way. The upside of this, and we did this in an earlier video in more detail, is that the runtime of a multiplication algorithm is theta n squared. So our default multiplication algorithm, our grade school multiplication algorithm, is n squared. The point of this video is to explore if we can do better. Okay, so we saw that this was n squared. We just revisited that now. All right, in 1952, a famous Russian mathematician, Andrei Kolmogorov, he conjectured that this grade school algorithm was the fastest you could possibly do for multiplication. Well, spoilers, he was wrong. And that's where we're going to bring in Karatsuba's algorithm. So we can imagine being Anatoly Karatsuba, maybe being quite a young man if he was listening to Kolmogorov's conjecture in 1952. He would have been about, I think, 13. Maybe 15, but he maybe knew of Kolmogorov's conjecture, saying that there was no faster way. Maybe he was inspired by that. Sometimes when someone comes out and says, hey, there's no way to do this, that inspires people to say, hey, I bet I could do that. And so maybe that's what inspired Karatsuba. And Karatsuba applied the design strategy that we have here, the one that we've looked at in a number of our videos now, the divide and conquer strategy. And let's just quickly go through it one more time to revisit the steps here. So again, the first step is the first step of any design strategy. Make sure we have a good formal problem, and we've already done step 1 on the previous slide. Step 2, identify subproblems. And so we're going to see in a second, our subproblems are going to be to split our bit string, our bit string that represents our number, in half. The challenge then is step 3. How is splitting our bit string in half going to help us? How does that help us do our math? And specifically in our problem, how does it help us do the product? How does it help us calculate the product? Say we figure that out. That was Karatsuba's clever bit. Remember, part 3 is where you need to be clever. That's where some creativity comes in. So say we have cleverly solved that problem. Then after we've done that, we can directly translate that usually into recursive code and a recurrence relation as well. And we've now done a lot of practice with recurrence relations. So hopefully once we get one, we're pretty comfortable coming up with a runtime for it. So, as I mentioned, this technique was applied by, this is Anatoly Karatsuba here, more recent photo. He solved this when he was quite young. And he came up with this algorithm, which again today is called the Karatsuba's algorithm. And then I also have here a picture of Volker Strassen, who is credited with another integer multiplication algorithm, one that I won't make a video of, or at least I don't plan to in the moment, maybe in the future, the Schoenhack-Strassen algorithm. So I leave it here as just a reference for something else to take a look at if you're interested. And this is Strassen here. We'll look at another of his algorithms here in the next video called Strassland's algorithm. So that's a little foreshadowing. Okay, so to get started here, let's do the splitting into subproblems that I mentioned here. Let's try and split our integers n and m into two parts, their upper and lower bits. Now again, I'm going to assume, as I mentioned earlier, that our n and our m are powers of 2, rather their size is a power of 2, so that when we split them in half we get another power of 2. So we're not going to have any floors or ceilings showing up here. We could be careful with that, but I'm going to assume for the moment that we've padded up. So, and when I say padded up, I mean padded with zeros, added zeros on it until the size is a power of 2. Okay, so again, if we split it in two, I'm going to split it into two pieces called the n upper bits and the n lower bits. But the n upper bits, we have to bit shift them over by n over 2 bits here. And here is where I could put the floor in if I needed to, but I'm actually going to leave it as just n over 2 bits here. That way these are the other half of the n over 2 bits. And we'll do the same thing for n. I'm using n here again, lowercase n. Again, remember, I'm assuming n and m have the same size. If they don't, well, again, we've padded them with zeros until they did. Okay, so we've got n upper, n lower. We got m upper, we got m lower. This is the first step. Now, the next step is probably to try and figure out how can we blend these together. And there's a little bit of algebra that we can do here. We could say, well, what is n times m using this expression? Okay, well, maybe making that clear, we'll have n upper times 2 n over 2 plus n lower, m upper plus, 2 to the n over 2 plus m lower. Multiplying them together, we're going to end up with 4 terms. So let's be careful. We're going to get the upper terms, n upper, m upper. Those ones are going to have 2 copies of this 2 to the n over 2 term. That's just going to give us 2 to the n. Okay. Now, I'm going to be strategic when I write the next terms here. We're going to have 2 terms. We're going to that mix the upper and the lower. And when we mix the uppers and the lowers, we're only going to get one of these 2 to the n over 2 terms. So I'm factoring that one out front, and we're going to see we're going to get the n upper times the m lower plus the m upper times the n lower. Okay, maybe I should rewrite that, but let's keep the n's first. Times the n lower times the m upper. So that's the upper lower and the lower upper. Well, that leaves us just with the lowers then, the n lower times m lower, and that one has 0 copies of this 2 to the n over 2 term, so it's not shifted at all. So this formula here is the basis of a self-reduction that we could come up with here. So this self-reduction that we have here, I've just written similarly on the slides, but just with in the self-reduction form. This would be only the recursive component of it. This self-reduction is a fairly well-known self-reduction. In fact, this was a self-reduction known to these 2 researchers I have here, Charles Babbage and Ada Lovelace. And if you haven't encountered them before, I definitely encourage you to take some time, go read about them on Wikipedia or somewhere else. They're important figures in the history of computer science. Some might consider them sort of the grandparents of computer science. If we consider sort of, Turing as the father of computer science, then these would be the grandparents. They operated in the 19th century, and they attempted to build the first mechanical computers. And in fact, together, while Babbage sort of was in charge of the machinery and building the machines, whereas Ada Lovelace was more thought about programming the machines. Actually, you might think of her as the first computer programmer. But they built mechanical engines, they called them, out of gears and so on. Mechanical bits that were popular at the time in that period of the Industrial Revolution. Charles Babbage had access to a lot of wealth through his family and access to machine shops, and he built a couple different engines. The first one was called the difference engine that worked with calculating values of polynomials. Very interesting work. And the second one was called the analytical engine, which was a more general purpose machine that unfortunately during his life he was never able to get working. But him and Ada Lovelace were two that worked on it, and they were aware of this recursive way of solving the multiplication algorithm. And so again, this is not this algorithm here rather is pretty well known. It was well known before even computer science became a formal discipline. However, if we take a look at this algorithm, and let's maybe look at it here, we could come up with a recursive recurrence relation to express the runtime of this. So let's assume that the input size is n. Remember, padded to zeros if we need to. I'm going to ignore the base case for a second and just worry about the recursive case and see here that we're going to end up with 1, 2, 3, 4 multiplications. So we're going to do 4 recursive calls. These are all recursive calls, right? They're written in the same form here. So these are all recursive calls, and each one, well, we said, is going to be half the size. All right, but then we're doing these adds. Now these adds along the way, plus these bit shifts, are going to be another possibly linear number of adds, order n number of bit operations. So I'm going to call that dn here. Now, in our last video, we took a look at the master theorem. And in the master theorem, we looked at a couple values. A, in this case, our A is 4. B, in this case, our B is 2. And then we compared, or we needed to compute, rather, log base B of A. So log base B of A, in this case, log base 2 of 4 is 2. And then we compared it, well, to the exponent here. I'm going to call it k in this case because we called it d in the other case, but I've already used d here. So I'm going to call it k. I'm going to say in our case k was 1, since it was sort of invisible there. And we compare the two. Now if one is greater than the other, then we use that as the exponent in our conclusion. So our t of n here must be in theta of, we're going to use this, n squared. So by the master theorem, quickly, we found that this recursive relationship that we came up with, this recursive algorithm, good algorithm, recursive, thanks to Charles Babbage and Ada Lovelace, they knew it too, but maybe at the time they did some of their own math and they were able to say, hey, wait, actually, this is n squared too. This will take n squared operations. So there's actually no benefit to doing it this way other than it's recursive. If you happen to exist in a programming environment where recursion is the only way to go, here's your way to do some multiplication recursively. One way, there's more than one way, but here's one. And it's a fairly efficient way. So what came from this then is a need to say, well, how can we improve this? And this is maybe where Karatsuba came in. Karatsuba probably didn't know the master theorem since it wasn't proven until 1990. But he may have known that if you were able to change this value here, it would change your calculation. And in fact, he might have thought, well, what if I change it to 3? Like, we could have gone further. If we change it to 2, we had our merge sort recurrence relation here, and we knew that that one was n log n. So maybe with a little bit of eagerness, he could say, if I could change this 4 multiplications down to 2, I've got myself to n log n, and hey, n log n is better than n squared. That sounds good. But where he was actually able to go was to reduce those 4 down to 3, and that will change this calculation in our log. Instead of getting log base 2 of 4, we get log base 2 of 3. Now this number, I don't really know it exactly, but I know it's between 1 and 2. So again, that's a better runtime than my n squared runtime that I just had. So maybe this is what's inspiring Karatsuba. He's saying, I want to eliminate one of these multiplications. Looking at the recurrence relation over there, there are 2 values that we probably need. And maybe he just started out ahead of time saying, look, I'm going to calculate these 2. I can't get away with it. So I'm going to calculate the upper times the upper, and I'm going to also calculate the lower times the lower. But I'm going to try and get this middle term here with only one multiplication. These 2 I'm doing raw. So now I need to do something with to calculate another one. Now he's called this third multiplication he's going to make, he calls it r. And for the moment, just bear with me, he does something kind of bizarre here. He says, let's take the upper bits of n. I'm going to add them to the lower bits of n. And then I'm going to take the upper bits of m, and I'm going to add them to the lower bits of m. And I'm going to take those sums that I made and multiply them together. Whatever that is, I'm calling it r. Now why would he think of this? Well, one reason he might think of this is maybe he just sat in a room for a long time and tried a bunch of things, and this is the one that worked. But he may have been inspired by the math that we just did, that we noticed that if we took this, 2 to the n over 2 plus nl, that's n. And again, our m was the same formula, n over 2 plus m lower. All he's done in this math here is he's deleted out these bits. Okay, well what does it give us then? Let's multiply it out and see what it gives us. Well, it gives us n upper, m upper, n upper, m upper, plus the upper lower, n upper, m lower, plus the lower upper, plus the lower lower. Okay. It's not exactly what we want. That middle term that we want is actually these 2. But you notice we've actually already computed P and Q, and this is P and this is Q. So if we actually go R minus P, that'll cancel out that one, minus Q, that'll cancel out that one, that gives us exactly what we want, the middle term of our recurrence relation. Okay, let's backstep a few things. How did we get there? Well, we did this bizarre multiplication. Now there's only one recursive multiplication here, but we did 1, 2 adds, and 1, 2 subtractions. So we sort of did -1 multiplication, but we ended up doing sort of +4 adds if we count our subtractions as adds as well. So the trade-off that Karatsuba's algorithm managed to do was basically to get rid of one of our recursive calls. Remember, this is recursive. And this here, we've increased the extra work we did. But the extra work we did here, we only increased the constant. We went from something like, I don't know, like 2n to like, I don't know, 8n. All we did is increase that constant, which means, well, we stayed in the theta n realm, and that's going to be what's helpful for us in finishing off our computation. So finishing our calculation, let's do this again with Karatsuba's algorithm here. If we were going to come up with a recurrence relation for it, we'd have our t of n, and again we said here, this time we're only going to do 3 multiplications, n over 2, plus we're still going to have dn. The only thing that's different now is this d probably got bigger, and I'm not as worried about that. So doing our master theorem here, we're going to have a equals 3 here, b equals 2, and again, remember that's going to give us this formula log base 2 of 3. Our k in this case was 1, so log base 2 of 3 is still bigger than 1. So that means our theta bound is this bizarre function, n to the log base 2 of 3. Now remember that this exponent is not an integer or a natural number. This is a irrational number. And this is going to be kind of that first bizarre algorithm that we have where the runtime is actually kind of bizarre. It's not n squared, and it's not n, and it's not even n log n. It's n to the power of log base 2 of 3. And this sort of expresses that we can get kind of bizarre runtimes for almost any power, any real number power that we could imagine here for n. We could probably design an algorithm with that runtime. Now most of those algorithms are probably going to be silly, but this is an actual algorithm for multiplication that carries out exactly theta of n to the log base 2 of 3 operations for large values of n. All right, let's maybe just revisit those values or those steps again. So we took a look at this recurrence relation and determined it was n squared. But then we took a look at Karatsuba's algorithm here, which processed 4 different multiplications. And again, we see the uppers and the lowers, and then this bizarre r value. But the product that we end up computing, we do r minus p minus q. And as we argued, that resulted in this nicer recurrence relation with only 3 recursive calls instead of 4. And this again gives us a better runtime. Okay. What I would like to do to complete is carry out sort of the last little bit and then do an example. So here I've just got some quick pseudocode. Again, translating a recurrent or a self-reduction into pseudocode is very straightforward. We haven't done too much here. We've got 3 base cases to handle, but then we're just computing our 3 products. Remember these are done recursively, so we're recursively calling multiply. Everything that's done here is addition or bit shifting. We're assuming this is bit shifting by our power of 2 here. Okay, so the example numbers that I've chosen here, I've written them in binary, but for some convenience, and I think most of us probably operate a little bit better in base 10, I'm going to write them in base 10 sort of in small here so we can see. So we're actually trying to compute here n times m is 20 times 35 is 700. Hopefully that's what we get at the end. So we'll double check. Okay. Now I've also kind of written them nicely here. This is going to be my n upper. This is going to be my n lower. This is my m upper and my m lower. And you'll also notice I've padded zeros in both of my cases here, as I mentioned, to make them of length 8, so that the n here, the size is 8. And remember, this n over 2 is going to show up a couple times, so that's going to be 4. Okay. Again, that's just going to make it easy. I'm only going to recurse down once. Technically, on the next level, we take our 4 bits and split them into 2, and then our 2 bits and split them into 1. That's a little bit, a little bit tedious. So I'm only going to go 1 level down. And instead here, so maybe I've already labeled my uppers and lowers. Now I want to compute my p. So my p was, what was it? It was n upper times m upper. So let's do that. Now my n upper here, lucky, that's 1. And my m upper here is 2. So it looks like I just get 2. Maybe I'll write that as a 2 if I like. Okay, my q, then were the lowers. We had n lower times m lower. And again, let's be careful here. So my lower here, this looks like it's 4. My lower here is 3. 3 times 4 is 12. Or, without having to do any sort of backwards conversion, we can see this looks like 100 to us, right? Well, multiplying by 100 in base 10 just means adding a couple zeros on the end, right? Well, that's the same as multiplying by 4 in base 2. So we took this number and just added 2 zeros on the end, and there you go, you got 12. Okay, The next number we wanted to compute was this number r, and r was n upper plus n lower, this sort of bizarre addition, multiplied by m upper plus m lower, same thing for m. Okay, let's kind of be careful with this. So here we're saying take the upper and add it to the lower. This is 1 plus 4, that's 5. It's easy math to do in binary too, there's no carry. Okay, so that's the first number here, 5. What about my second number? My second number here we have upper is 2, lower is 3, that's also 5. All right, and 5 times 5 then is 25. Okay, again, we could do this in binary, but I'm just going to do a quick conversion in my head here. 25 is a 16, an 8, and a 1. Okay, so this is my 25. Okay, remember this was a 12. So now what we actually needed was r minus p minus q, and sometimes this is the step that we sometimes forget when we're doing Karatsuba, is we've calculated our middle term here, but not quite. We need to subtract off those other values. So it looks like here we've got 25 minus 12 minus 2. I'm pretty good with my binary math when I'm doing additions or multiplications, but the subtraction, I haven't got that all down, so I've really just converted this in my head. I've got 25 minus 12 minus another 2, that's 14 I'm minusing off there, that looks like it's 11, and 11 I know is this in binary. Okay, an 8, a 2, and a 1. Okay, so I've got my 11 here. That was my middle term. Remember, the whole value now, my n times m, is equal to my p times 2 to the n plus my r minus p minus q times 2 to the n over 2 plus just my q. So now I just want to know what these three values are. Now usually I write these together as a sum here. So I'm going to start with my p. Where's my p? Here's my p. It's 2. I'm going to be careful. 0, 0, 1, 0. That's my p. I'm leaving those leading zeros on there. Now remember, this one's shifted by n. n is 8. So that means 1, 2, 3, 4. 1, 2, 3, 4. 8 zeros after. Now my my next value, my r minus p minus q, that was this one. Now I'm going to be careful here. This one shifted over by 4 zeros. So when I write this in place, it's 1, 0, 1, 1. Okay, finally, then I finish with my q. That's this one here. It's not shifted at all, so it just goes here, 1, 1, 0, 0. Okay, now you could get some interference, although in our example we didn't. So our total value here, summing these three values, is this value in binary. Okay, now what is this value in binary? Well, I can give you a hint here. This is 2 to the 9, so we get started here. This is 512. 512. So that's 256, so that must be a 128. Okay, where are we at here? That's a carry. Okay, looks like we're at 640. Okay, that's 128. So that's a 64, so that must be a 32, so we're at 672. That's a 16, so now we're at 688. We got an 8 on there, that puts us at 696. And a 4 on there puts us at 700. Hey, that's what we were trying to get. Looks like Karatsuba's algorithm worked out for us, and we computed it correctly. Okay, this is a fun little exercise to do with Karatsuba. You can actually do it in decimal too. It's just even easier. Okay, we would split this into 2 and 0, 3 and 5. Do the math. Try that out as a side calculation. Although, of course, in the machine we do it in binary. So here we've done the calculation in binary. All right, so this video we've taken a look at a faster way to multiply two integers together using Karatsuba's algorithm. Faster than the normal way, which was theta of n squared, our new method is theta of n to the log base 2 of 3, which is kind of interesting. It's kind of a bizarre state, as I mentioned, and it raises a situation here. So let's consider this again. So say we have this n squared algorithm. Karatsuba comes along and says, hey, I've got this clever way where I've reduced one of my operations, so I've been able to get down to log 3. Now, say Karatsuba was proud. He wasn't proud. He didn't do this. He didn't say, well, now I've got the best algorithm. Take that, Kumulgarov. You thought you had the best one. Now I think I have the best one. Actually, I think Karatsuba was much more humble than that, saying almost the opposite, saying, I bet you there's a better one. Now, why is there a better one? Well, we could have split our number n. We split it in 2, but we could have split it into 4. The upper uppers, the upper lower, the lower upper, and the lower lowers. If we did that for n and m, we could get some bizarre recurrence relation. Multiplying it out, we'll end up getting 16 terms, each one n over 4. Notice log base 4 of 16 is 2, so we're still in that n squared realm. Okay, but if we could delete one of those, get log base 4 of 15, well, log base 4 of 15 is probably not better than log base 2 of 3, but maybe if we got it down to 14 for 13 multiplications, meaning maybe someone clever like Karatsuba could come along and shave a little bit more off this exponent. So what I'm sort of thinking of ourselves as doing here is we've got an actual runtime that we're going to get to down the road, and what we're doing is we're kind of shaving a little bit off. Maybe a more clever algorithm is going to come around and we're going to get log, like I said, base 4 of 13 or something like that. And then someone says, well, I didn't need to split it in 4s, I could have split it into 16s. And now I'm getting something n to the log base 16 of 256 would be our normal case. That would give us 2. But let's say we shave that down to, I don't know, 201 or something weird like that. Now, the math going into building that algorithm is much trickier. Instead of just reducing one multiplication like Karatsuba did, you'd have to reduce a whole bunch, and you'd have to be more clever. But if you're doing it, you're maybe able to keep shaving a little bit more off. And you might think, well, where are we aiming? If we took this to infinity, if we allowed infinite mathematicians for infinite years to work on this algorithm, how might we get it? If we kept using this strategy, we might shave it all the way down. And there's a couple instincts of where it might go, and hopefully you have an intuition here. Now, some of you might say, well, we could shave it all the way down to n. Now, I think that's a little ambitious. And with a little bit of practice, you might say, I don't think I'm going to get there. But as close to n as you can get would be adding on this log n, right? Now, log n is smaller than any exponent, n to any exponent, any polynomial you can multiply by here. So remember, n to the 1.5 is like n times n to the 0.5. But log n is smaller than any exponent you could put here. And this might be the target that we're aiming at. Well, the other algorithm that I looked at here, Schoenhag-Strassen, I mentioned, and we're not going to look at it here, actually gets us as close as we can get without getting there. It adds on this extra factor here, log n. Now, log n is a very small or slowly growing function, very small number. Okay, it's log of a log n, right? But this is pretty close, so if you're interested, I recommend taking a look at that other algorithm. Now, very recently, in the last couple months, I noticed some algorithm, or a couple papers out there that suggested that they've even shaved this off too. Now, I haven't verified those algorithms, I haven't taken a look at that paper to take a look, but certainly the instinct would be that we should be able to try and find this n log n algorithm if it's out there. And of course, researchers are still working on it. Now, I've presented Karatsuba's algorithm, which doesn't have an n log n runtime, n to the log base 2 of 3, again, as a means of studying the divide and conquer design strategy that we've been looking at in a number of videos. Okay, that brings me to the end of the discussion of Karatsuba's algorithm. I do want to, in my next video, take a quick look at another related algorithm to Karatsuba's called Strawson's algorithm for matrix multiplication. All right, thanks for watching, and we'll see you in the next video.